Welcome to this talk on SimLoss, a loss function that incorporates class similarities into the training process of neural networks. My name is Konstantin Kobs and I'm from the University of Würzburg in Germany. There is a saying which is, roses are red, violets are blue, both are somehow similar but the classifier has no clue. Let's suppose we have this neural network classifier which does image classification. It gets this image as input and is supposed to output the corresponding class violet. If it predicts violet, everything is cool. But if it predicts car, truck or train, it is just the wrong prediction, as these classes are not at all similar to violet. However, if the classifier predicts rose, it is still the wrong class, but the mistake is less severe than predicting car, truck or train, since a rose is a flower, such as the violet. We can see that there are classes that are more similar to each other than to other classes. Our idea with SimLoss is to use this similarity information to punish the network less for misclassifications of similar classes than for very different classes. This way, the network should learn to predict similar classes if it misclassifies an example. In this case, if it misclassifies a violet, it should predict rose more often than very dissimilar classes such as train or truck. SimLoss is a modification to the categorical cross entropy, which does not take other classes into account, but only looks at the predicted probability for the target class index yi. SimLoss generalizes categorical cross entropy by incorporating a matrix S denoting the similarities of all C classes. 1 means that classes are identical, while 0 indicates that the classes are not at all similar. Given this matrix, the loss is larger if the network outputs high probability for dissimilar classes and thus learns to predict more similar classes in case of misclassification. If the similarity matrix is the identity matrix, categorical cross entropy and SimLoss are identical. However, we can now apply class similarities in our training. In our example, a similarity matrix could look like this. The similarity of violet to rose is higher than to car. This matrix is manually created for this example. But can we do this in a more automatic way? We propose 2 generation methods to incorporate different types of background knowledge about the classes. First, class order. If the classes have an inherent order, classes that lie near together are more similar than classes that are farther away from each other. Thus, we introduced this formula that has a hyperparameter called the reduction factor, R, which denotes the decay of similarity with the distance of classes. Second, for general class similarities, we can use a similarity measure of our choice. We could use this directly in the matrix, but sometimes it is desirable to have more control on the resulting matrix. We therefore introduce a lower bound L, which cuts all similarities below it and then scales all resulting similarities to a range from 0 to 1. This way we can control the sparseness of the similarity matrix. To test SimLoss and the generation methods, we conducted multiple experiments on 2 tasks, age estimation and image classification. Age estimation is an ordinal classification task, where the network gets an image of a person's face and predicts their age. Classes denote ages and thus are similar when lying next to each other. For example, ages 30 and 31 are more similar than ages 30 and 60. Thus, we can use the similarity matrix generation technique incorporating class order. In image classification, the classifier gets an image and predicts its class, such as rose and car. Some classes are semantically more similar, so in our case, we calculate the class similarity using the cosine similarity between word embeddings of the class names. With this similarity measure, we can use the previously described technique to generate the similarity matrix. For the age estimation experiments, we use 2 datasets, UTK phase with 90 classes and the AFAD dataset with 61 classes. We used a CNN classifier that was previously used for age estimation. We tried different reduction factors from 0, which is equal to categorical cross entropy, up to 0.9. To evaluate the results, we used the common metrics accuracy, mean absolute error, and mean squared error. While accuracy only measures exact matches, the other metrics give a better sense for how far off the prediction is. The results show that reduction factors that are not equivalent to categorical cross entropy are able to yield significantly better results on all metrics. However, there seems to be a trade-off when choosing the reduction factor based on the metric. For example, large R yields significantly worse test results for accuracy. For our image classification experiment, we used the CIFAR100 dataset and the Linnet CNN classifier. As a similarity measure, we took the class names and converted them to word embeddings using the word-to-vec model trained on the Google News corpus. Then we calculated the cosine similarity between these embeddings. We experimented with different lower bounds from 0 to 0.99, which is equivalent to categorical cross entropy. As evaluation metrics, we used accuracy, which measures the exact predictions. Additionally, each class in CIFAR100 has a superclass. For example, rose and orchid both have the superclass flower. We then check how often a class with the same superclass was found. This superclass accuracy is at least as high as accuracy, as predicting the correct class also yields the same superclass. Thus, we also looked at examples that were misclassified and calculated the superclass accuracy of these examples, which we call failed superclass accuracy. The results show that, again, lower bounds that are not equivalent to categorical cross entropy yield better results, but also optimizing the validation set to the failed superclass accuracy yields significantly worse results for accuracy and superclass accuracy. So, there is a trade-off. Setting the hyperparameters R or L close to categorical cross entropy usually improves accuracy and thus exact matches. However, hyperparameters far away guide the network to focus more on similar classes and thus inexact matches. You therefore have to choose what metric is more important to you. We therefore wanted to analyze the network's output given different hyperparameters. For this, we calculated the predicted probability distribution for all examples in the UTK phase dataset. We then plotted the mean predicted probability distribution to see how the output changes for different hyperparameters. The plot on the left shows that the more the reduction factor diverges from categorical cross entropy, there are fewer but larger spikes in the output for certain classes. Doing the same procedure for the H class 30 on the right, the model usually predicts two classes that are not far from the correct class. Thus, larger reduction factors let the network focus its output to a few representative classes. In conclusion, SimLoss enables us to incorporate knowledge about class similarities into the training of neural network classifiers by creating a similarity matrix. We propose two similarity matrix generation techniques, but in general they can be created manually, semi or even fully automatically. Our experiments have shown that choosing the right hyperparameter improves the network's performance on different metrics. The network focuses its outputs to representative classes if a hyperparameter diverges from categorical cross entropy. Thus, there is a trade-off between optimizing the network towards exact matches or inexact predictions that are less severe in case of misclassification. This concludes the talk on SimLoss. If you are interested in more details, check out our paper. We also provide a PyTorch implementation of SimLoss, which you can check out in our GitHub repository and use as a drop-in replacement for categorical cross entropy.